Okay, good morning, guys. It's 11 o'clock. Welcome back. Please, if you can't hear me, do let me know. Uh, okay, okay, Mackenzie. Uh, okay, I've gotten your message. Um, I think you can maybe right click and then check like there's rename there. When you put it on your profile, you see rename. If it's possible, then you should change it. But if not, that's okay. I'll just check it after the class. Okay, so please, any comments before we start? Okay, then let's continue from where we left off. It's just, oh, okay, that's okay. I mean, with technology, sometimes these things happen. It's okay. So see if you can rename it. If you can't, I'll check it out with the, what do you call it, with attendance thing. I'll sort you out. So I'll look at the chat and check it out. Okay, then let's move on. So last time when we met, we were looking at the 2.1, right? So we're looking at the tangent and velocity problems. Now we finished discussing what the tangent problem is, and we started with an experimental data. We said that when you're given this function, usually when you're given a function which is like this with an x in it, we can plug in whatever x we want, right? We can plug in whatever x. But sometimes it's not always the case that you get a function with an explicit formula, right? Sometimes you obtain experimental data like this. This is not a function. You can't plug in any t that you want. The t's have already been obtained. So for that one, if you want to compute the slope, we said one way is to average the adjacent secant slopes, right? The adjacent secant slope at the point of interest where you're interested in the tangent line, right? So we did that, and we did this computation and we got this, right? So the adjacent ones, we're looking at the slope of the tangent at what? This point, the 15, 250. So we looked at the adjacent secant slope, which are between 10 and 15 and between 15 and 20, right? So this is the 21, this is the 10, and then we struck the average. So that's negative 38.8 and then negative 27.8, right? So we strike the average and we get this. So this will be the estimate for the slope of the tangent line, right? Please, I hope you're okay on that. That was the last thing we did. Now moving on, the second approach is we can get an approximation of the what? Of the graph of the problem. So what I mean by that is, I'm just saying that I use Desmos to obtain what you're about to see, right? So let me show you something here. Perhaps I should share like so. Yeah, to narrow it a bit so that you can see it well. Okay, so now what I was saying is, another way is we can get an estimate, an approximation for what the actual graph is. Now, what do I mean by that? Now, for this one, you're giving points, right? You're giving a point at 5, you're giving a point at 10, you're giving a point at 15, you're giving a point at 20, 25, and 30, right? These are points. You're not giving a function. But going back to the question, we are told that the tank holds a certain amount of water and it's draining from the bottom of the tank in half an hour. Now, the problem doesn't say anything about us filling it up again, right? So if you have a tank, then it's draining, right? Either we plug it and it stays the same, or it keeps flowing. So either it drains or the water level stays the same. It's not increased, right? It's always going to either decrease or remain the same, right? So this gives me an idea that, well, I can kind of like estimate what the graph is, right? What the graph is. I know that between experimental points, like between 10 and 10, like for example, between 5 and 10, the only possible case is this is going to reduce. The volume is going to reduce because it's decreasing, right? It's draining. There's no water being pumped into the tank, right? So it's draining. So I can estimate that, oh, between this interval 5 and 10 is supposed to decrease, right? So more like decreasing. Between 10 and 15 is decreasing. You see, between 15 and 20 is decreasing. From 20 to 25 is decreasing. And 30, nothing is in the tank, right? So I can obtain this graph from here, right? So that means that I can try and get an estimate. So this is not the actual graph. What you see here, the dashed lines here, it's not the actual graph. It's just the estimate, right, of what the graph of the function is, right? The actual graph is here. The actual points which are given were these points, this one, this, that, and that, right? But this is just an estimate of what is happening, Please, you see. So if you have a clear idea of what's happening in between, you can just get an approximation of the actual graph. Now, when you get the approximation of the actual graph, you then try and get an approximation of the tangent line. In other words, what would the tangent line look like if the graph is like so, right? So if the graph is like this, then the tangent line will look like this, right? So you're looking at the tangent at this point, right? Tangent at this point. So the tangent will just be this line. It's an approximation, as I said. This is not the best at this point, but that's this is better than nothing, right? This is better than nothing. So this is an approximation. So when you check your homework, it will give you several answers that you can plug in. It will give you a range of answers. It's not just one single answer because this is an approximation. So this is the approximation of the tangent line, right? That's what you see here. Now I did this rectangle so that you see that I'll be interested in measuring like the height of the triangle here, and then the kind of like more like the length right here, down here, right? So that I'm able to get the rise over run. Right, the rise over run. So that'll give me the slope of this approximate tangent line that I drew, right? So I can say that here is the rise of that line, and here is the run. So that means that the estimate for the tangent or tangent slope will be equal to what? The rise. Let me write this first. Rise over run. So what is that? So the rise, I've measured that to be 225. And then the run, I measured that to be 6.7. Right, so when you do the math on this, you get your approximation. So which is like 225 divided by 6.7, which is like 33.58, say to 2, 33.58 approximately, right? So this is it. Please, are you okay with this? Any questions? Okay, so as I said, this is not the best. This is the best we can do. We are just approximation, approximating, right? It's just an approximation. Okay, please, anybody needs time here? Okay, so you see that in your homework, right? In your homework, problem 3B is going to ask you to use the graphical method. So I just created this thing to help you solve that, right? So let me perhaps see this link. I think it will come on when I do this. Shift. Let me share like so. Wait, someone sent me something in the chat. Where is it? Chat. Why are those measurements chosen on the triangle? Okay, so why are those measurements chosen in the triangle? Please, I hope you can see the PowerPoint. Okay, so what I'm saying is, I'm choosing that because it's kind of like an eye. You're gauging with your eye what the tangent line will be like. You see what the tangent line will be like. It's just an approximation. So the line I'm actually referring to is this one. This is the tangent line. This line that you see here. You see this line. That's it. But I drew the triangle here so that I can measure like the size, like the rise of the line over the run. Do you get it? So that's why I'm getting the measurements, right? The rise over the run. So it's not a triangle I'm doing. I'm just is this line, is this tangent line, and I'm doing that with like an eye, a measurement. That could be an approximation of the tangent. And then if that's the line, then what is the rise, and then what is the run? So that's where I'm getting the values from. Please, I hope that's okay. Makes sense. Okay. Let me see. Nice. Okay. So as I was saying, on your homework, right? Before you come here, on your homework, I drew this for you guys. Like I created this in Desmos. Please, I'm sharing the Desmos. If you can't see, do let me know. So I know it's going to be something, right? Because you need the points, you need to graph it to be able to gauge how the tangent line will be. I decided to create this for you guys, right? So we want the tangent at a point S1, S2. So look at your problem and look at what S1 is and what S2 is and plug it in here. So you just edit this, right? So in my case, the problem that I saw, I was looking at S1 being 3 and S2 being 23.1. So when you enter this here, right, say 3 and 23, so you enter the number here, right? And then you enter the Y coordinate also here, right? So just clear this, say if it's 3, 2.5, you just do this, 2.5. And then you enter the corresponding Y coordinate here, right? So you can edit this one. And then when you fill that in, it says enter your table values here. Leave out S1 and S2 since you entered those above. Because you've entered S1 and S2, please don't enter anything in place of S1 and S2. So you replace the other ones, right? So 0 at 1, at 2, 4, 5, 6, right? So you fill in those. So that'll give you a complete table, right? And automatically it will grab the points for you. It will grab the points. And we need a tangent line at that S1, S2, right? So ignore this. You don't have to edit anything here. And then this one says, I use this to obtain the smooth line between the points. Do not be concerned about this. So as you know, with experimental data, the points it's just points. It's not a graph. It's not a line, right? It's not like a smooth line. But I did a smooth line so that we can get an approximation of the tangent line, right? And this is what I'm using to get a smooth line. That's why I said, do not be concerned about this. I think I have something in the chat. Give me a sec. Chat. Sometimes I can't see. Okay. The chat just disappeared. Okay, yeah. So let me see. Can you copy the paste into the chat so we can save it for? Yeah. So I'll post the slide, right? I'll post the slide. So either you will be able to see, you'll be able to access this. You'll be able to access this. Okay. Yeah. So it's for you guys. So you'll be able to access this. You just type this link in. You get it. Yeah. Okay. So now let me go back to the Desmos. Please, can you see the Desmos? Okay, cool. So when you fill in the table and then you have the smooth line will graph automatically. You don't have to be concerned about this, right? And then this will also be automatic. You don't have to worry about any of this, right? So at this point, all that you have to do is you see the tangent line. It says move this point for the tangent line, right? Green to touch the curve only once, right? So because it's a smooth line, your tangent line cannot be something like this. You see, that would be wrong. So an estimate of the tangent line will be somewhere here. And you see that as you turn it, the M here is shifting. You see, as I turn it, the slope is shifting. You see? So when you get a tangent line, which is just about, you could say this one, just about here, then your answer will be here, 18.23. So that's what you have to pick. That'll be your answer. Right? So this is an estimate of my tangent line. So it is like, so no, this one crosses it. Make sure it doesn't cross it twice. So let's say it crosses somewhere here is tangent. Yeah. And then you pick this answer. So 16.8. Are you okay? So that's how you do the homework. That's question 3B. Right? So just get the tangent line. Of course, make sure it doesn't touch it twice, like somewhere here. And then you type in your answer. Okay. Please, any questions on this? Okay. So that's it. So that's it for the homework. Okay. Let me go back to 2.1. Okay. So if there are no questions, then let's move on to the velocity problem. Now, for the velocity problem 2, we are going to introduce this with an example. We said, suppose a ball is dropped from the observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. All right, find the velocity of the ball after 5 seconds. Let me see, do I? Yeah. Someone is asking if there's a range of correct answers on the homework. Yeah, it will be a range of correct answers. So someone could type in, but it gives a margin of error. It won't let you go far beyond, right? It will have a margin. So let's say, I'm just guessing, but this is not the correct thing. They'll say, if you plug in 16.1, it will be correct, 16.2, it will be correct, 16.5 will be correct, probably 17.9 will also be correct. Like within that range, it will give you like a range, right? Which you can get correct. So that's the statement. It's not one single answer, yeah. Okay, so now back on the PowerPoint. So as I was saying, suppose we drop a ball from this upper observation deck, 450 meters above the ground. Find the velocity of the ball after 5 seconds. Now, for this problem, right, the question is asking us to find like an instantaneous velocity, right? So say, let time pass, and then at exactly 5 seconds, at exactly time 5, what is the velocity of this ball? That's what the question is asking about, right? At exactly time 5, what is the velocity? Now, the formula to try and compute these things was obtained by a man named Galileo, right? Galileo Galilei. Now, this man dropped he dropped some stuff from the Tower of Pisa, right? In Pisa in Italy. And he formulated a formula. He said, by the law of falling bodies, Galileo's formula says at any point in time, right, the position function of a falling object is given by 4.9 t squared, right? So there's Galileo's law of falling bodies, right, of falling bodies. So if something is falling, then this formula is given by 4.9 t squared. Okay, so now this question is asking for the velocity at an instant time of what? Of 5. So at exactly time 5, what is the velocity of this object? That's the question. But the problem with this question is, just as we had it for the tangent problem, for the tangent problem, we were trying to find the slope of a tangent line, but we had only 1 point. You see, we had only 1 point. A similar case happens here. In this question, you're trying to find an instantaneous velocity, but it turns out that we don't have a formula for instantaneous velocity. We rather have a formula for average velocity. Average velocity, and that one needs intervals. It needs 2 time intervals, not a single time point, right? Instantaneous velocity is a velocity at a specific time. So say at time 5, what is the velocity? However, average velocity computes the velocity within times. So what do we do? Well, because we know of average velocities, we know how to compute average velocities, we can perhaps compute times closer to the 5, right? So we need the instantaneous velocity here. So what do we do? Because we have the formula for average velocity, which is change in position over time elapsed, you compute, say, you get 1 point, say 5.1, right? Now, if you have 5.1, then we have 2 time points, so we can compute the what? The average velocity. And then we compute something closer. So say 5.5. Compute closer, right? So you compute average velocity closer and closer. You can also measure average velocity from this side too. So you say you have 4.9, 4.999, 4.99999. Now, looking at the velocity, average velocities obtained for the 2 intervals, so from the left and from the right, you can then guess what your instantaneous velocity at that time 5 is. You see, so these problems are more like the same. The tangent problem and the velocity problem are the same. For tangent problem, we are trying to find the slope of a tangent line, and we try to guess that value by what? Getting the slope of secant lines and getting it closer. You see. On the other hand, for the velocity problem, we are trying to find instantaneous velocity, but you're trying to obtain about getting what? Average velocities, getting closer and closer. You see. So the velocity problem is just the same as the tangent problem, but the function is just the position function, not a curve. So under the tangent problem is a curve. Under the velocity problem, that is the position function. And then under the tangent problem, you're looking for the slope of the tangent line. Under the velocity problem, you're looking for instantaneous velocity. Under the tangent problem, you're using secant slopes to estimate the tangent or the slope of the tangent. Under the velocity problem, you're using average velocities to estimate the instantaneous velocity. So they are connected. It's just the change in the function name, but the problem is the same. And that's a very good thing to know. Please, do you get it? So it's not different. It's just that the function is now called a position function. Slope of a tangent is now the instantaneous velocity. Secant lines are just the average velocities now. You see, that's the connection. Okay, please, any questions here? So similar to what we did for the tangent problem, we get a table like so, right? So average velocities are computed within an interval. So within 5 and 6, they computed, that's 53.9. Within 5 and 5.1, they computed 49.49. Within 5 and 5.05, 49.245, and so on. Up to 5.001, which is 49.0049. So it's fair to estimate that this one is approximately 49. But they don't have it for this one is from the right, from bigger values. So we started from bigger values on this side. So all these numbers are to the right of 5. You can also do it from the left of 5 and compute it. You see that those two will agree on what? 49 meters per second. As I said, it's just a guess for now, right? In your homework, you can probably type in 49.001 and it will say you are right. You can type in 49 point maybe 1. One will even be say you are right. Right? It gives you a range of values because you are guessing at this point. That's the best we can do.
Do you mind going back to the table, please?
Is someone asking a question?
Yeah, do you mind going to the table, please?
Yeah. I'm not done though. Let me try and go through some of how they obtain this. Okay. When you're done, please do let me know.
Yeah, thank you.
Okay, you're welcome. Did anyone else has? I think I overheard someone speaking about this. Okay, so now I already have just explained how this works, right? How they relate. Now let's look at how we compute the average velocity. How do you obtain the average velocity? So for average velocity, the formula is given by changing position over time elapsed, right? Changing position. So you need 2 time intervals. Now on this slide, I'm telling you the time intervals you need, right? So I give you 5 and 5.1. In your homework, it's going to say, let's say it starts at say 5 and it lasts 0.1, right? So if it says compute the average velocity starting at 5 and lasting 0.1, it's still the same. It means 5 and 5.1 because when it lasts 5.1, when it lasts 0.1, the new time is 5.1. Are you okay? So note the two, like the vocabulary for that. Right? If it says T, it starts at 5 and it lasts 0.1, it just means between 5 and 5.1. Right? So it relates to this. Now for this one is direct. It says from time 5 to 5.1. So we know average velocities or change in position over time elapsed. In this question, by Galileo's law of falling bodies, we know the position at any time. The position at any time is given by what? 4.9 t squared. Now you don't need to memorize this. If you have to give you something like this, I'll give you the function. I'll give you the function. So if this is this, then the change in position, what is change in position? You're looking at within time intervals 5 and 5.1, right? So how do you compute it? Change in position, that'll be the position at 5.1 minus the position at 5. And then all of what? Time elapsed. So the time elapsed is 5.1 minus 5 dc, right? And then what is S of 5.1? Because we know S of t is 4.9 t squared, S of 5.1 is just 4.95, 5.1 squared. You see, this is it, right? This here is S of 5.1, right? And then S of 5 is just 4.95 squared, you see. And then the 0.1 is just 5.1 minus 5, right? So that'll give you your 49.49. So that's how you compute average velocity. Please, are you okay? Any questions? Okay, so you compute closer and closer time, briefer and briefer time intervals, and you estimate the instantaneous velocity. And that's all on 2.1. Okay, please, any questions here? Are you okay? Any part you don't understand on 2.1 that you want me to go over? Okay, then that's it for this. Okay, so save. I'll be posting the slides too, so. And this one is just definition. That's why you're using more of the slides. We'll be working a lot more like on a whiteboard and stuff. For now, we'll be doing just slides most of the time because you are just explaining concepts. Okay. Please, I'm sharing the PowerPoint of 2.2. If you can't see, do let me know. So 2.2. Now, we just saw that when you are trying to compute instantaneous velocity or the slope of a tangent line, this concept of limit comes in because the slope of the tangent line is the limiting value of the slope of secant lines. The instantaneous velocity is the limiting value of average velocities, right? So we made these observations. Now, this means that the concept of limit is very, very important in these two problems. So we are just now going to shift our attention to finding or identifying what the limit of the function is. And we will develop techniques on how to obtain the limit of a function. Because the guessing thing is not a perfect thing. As you all know, guessing is not a perfect thing to do, right? So let's get more concrete ways of getting the limit, right? So that's what you're going to look at. You're going to start here, and then we develop more as we go. So 2.2, the limit of a function, right? So we are just turning our attention to limits in general. Now, for this section, I'm going to start by introducing the numerical method. We've already seen the numerical method at work in 2.1, but we also include the graphical method here too. So 2 approaches. Now, for the numerical method, it's just for seeing how things go. Sometimes you use it to confirm some principles, but you won't be doing this on an exam, numerical, right? The one that you saw in 2.1 that we used to guess. Okay. Now, the graphing method, that one will be with you, to stick with you for the entire course, right? Okay, so we start by investigating the behavior of this function. So you have s squared minus s plus 2 for values of x near 2. So I'm going to use the numerical method and graphical method to compute the limit, right? And you're interested in near 2. Okay, so for this one, how do you write it? We learn how to write the notation. So it's more like limit, like so. And then what are we approaching? Near 2. So x, and the independent variable here is x. So x, and then you do the arrow 2. And then the function, what's the function? It's s squared minus s plus 2. So we are trying to find what this limit is using the graphical method. So that's how you write it out. And then the numerical. Anybody needs time here? Okay. Now let's move on. So looking at the numerical method, we know that you're trying to find the limit as you approach 2. So you want to find the behavior of the function for s values close to 2, right? So 2. Now we saw in 2.1 that you have to check from the right and then from the left, right? So these 2 tables that you see here are illustrating those 2 approaches, whether you're approaching from the right or from the left. Now, if you're approaching from the right, then the numbers have to be a little bit bigger than 2, right? If you're approaching from the left, then the numbers have to be smaller than 2. So looking at this table, you see it's kind of like it's 2 tables here, right? So looking at this side, you see 1, they tried 1, right? 1.5, 1.8, 1.9, 1.99, 1.95, 1.99, 1.995, 1.9999, right? And they are computing the value of f of x. So for each of these x's, they plug it in the f of x. Now let me write f of x back. S squared minus x. S squared minus x plus 2. Yeah. So for each of these values, say 1, they plug it in. So 1 squared is 1, 1 minus 1 is 1, and then 2. That's how they got the 2, right? And then for 1.5, they plug it in, right? So that's 1.5 squared minus 1.5 plus 2. That's what is giving us the 2.75, and so on and so forth. 1.999, you see. Okay, so we see the pattern. Now, what about the other side, from this side? So this one is from the left. So these are smaller values. So this one is from the left of 2. Let me say approaching, yeah, or approach from the left of 2. Now, we can also take numbers bigger than 2 and check that also. So you try 3, that's giving us 8. Try 2.5, that's giving us 5.75, 2.2, 4.6, and so on and so forth. Add 2, getting closer and closer to 2, right? 2 is here, getting closer, closer, right? So the closest they picked was 2.0001. And that was giving us a function value of 4.003001. So this one is, you're approaching from the right of 2. Now, with the numerical technique, after you approach very, very small values, like you approach the number of interest, then you check the numbers. So look at this one and look at that. What would you say our best guess will be? What is this limit approaching? Perfect. 4.
4.
Awesome. Thank you, guys. Thank you so much. Yeah, that's correct. Now, in this class, I will encourage you to always speak your mind. Feel free to make your mistakes here, and then we learn from it and move on, right? So feel free, speak your mind. Now, let's go. It's 4. I agree with you, right? It's 4. Looking at this number. So we estimate that, oh, this is going to be 3.97. It's going more 3.9 something. And this one is 4.03. Yeah, so numerically, I can say that my best guess is 4, right? So that's how you do it the numerical way. Please, anybody needs time here?
No, but could you go back to the last slide for just a second, please?
Sure.
Okay, perfect. Thanks.
You're welcome. Anybody else needs time here on this slide? Okay. So as I said, you won't be using the numerical to compute any of your limits, right? But that's the process you started. Now, one other way we said we could do is what? To use the graphical way. The graphical way. So for the graphical way, how do you do it? Now, don't forget you're trying to find this. So limit as s approaches 2, and then of the function s squared minus s plus 2. Right? So for the graphical way, you have to graph the function. So that's what you see here. That's the blue. Right? That's what you see here. And then you locate what you are approaching. We are approaching 2. Right? So where is 2? So locate 2. Now 2 is on the x-axis. So it is 2. Right? That's the graphical way. Approach 2. Okay, 2 located. And then you track the behavior of the graph as you approach the 2. So approaching the 2, let me see. Oh, the function is going down, 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 down. And then, then look at here, right? As it approach, look at this spot. Never cross the 2, right? If you're approaching from one side, you have to approach from the 2 sides, right? But for each of the sides, don't cross the 2, right? I can observe the function going here. Oh, okay. Up to this point. So I can say the limit is approaching what? From the right is what? It's 4. What about from the left? So track the graph. It's going up, 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 up. Oh, okay. Before I cross 2, it turns out that this one is also approaching 4. So the 2 meet at 4. You see, that's how you see those arrows on the 4. So they are both approaching 4. You see, they're both approaching 4. That's how you do it the graphical way. So just track the graph from the 2 sides and see which number is approaching. Never cross the number that you are taking the limit towards. Right? So you never cross 2. So whether you're approaching from the left or right, never cross the 2. So from the right, you track it to 2. Right? So it's more like you're reading the number at 2. You're reading the number at 2. That's the idea. So that's the graphical way. So here, I will safely say this is 4. So that's how you do it graphically. Please, any questions on this? Okay. Anybody needs time here? Okay. So that means that we can get the function to be as close to 4 as we can, as we take values of x to be close and close to 2. So we therefore say that the limit of the function, right, which is f of s giving us s squared minus s plus 2, as s approaches 2, is equal to 4. That means we can make f of s as close to 4 as possible as we get closer and closer to 2, right? So that's how we say it. So this is the notation. That's how we write it. So the limit lim s approaches 2, and then the function here, and then equal to the number, so 4. Okay. Please, any questions? Now, when you're able to get a number like this, you say the limit exists. Right? We got 4, so we say the limit exists. That's a terminology. Right? So the limit exists and it is 4. Okay. Anybody needs time here? Now, let's look at the actual definition. So this is the intuitive definition of a limit. So suppose f of s is defined when x is near the number a. Now, this thing is important, near the number a, right? When you are taking the limit, don't forget that we don't plug in the exact point, because if you remember, at the tangent problem, say when we were looking at the tangent at the point P11, we never looked at finding the slope of a secant line passing through 1, 1, 1, and 1, 1 again. We always look for points around 1, right? We never pick the same P11 twice, right? That's what this is saying. The function has to be defined near the number a, near, right? So if it's 2, the function only needs to be defined near 2, not necessarily at 2. The function could be defined at 2, that's fine, but we need it to be, most importantly, defined near 2, not at exactly where you are taking the limit of. So if you are taking the limit as you approach 2, we need it near, so it has to be defined here and there, not necessarily at 2, right? So that's important. So if the function is defined near 2, and then we take the limit either using the numerical or the graphical, and we get L. Then this is how we write it. So we do limit as S approaches A of f of s is equal to L, right? So you read as the limit of f of s as s approaches A equals L, right? Or you can say limit as s approaches A of f of s is equal to L. That's the same thing. Now, when do we say this is true? If we can make values of f of s arbitrarily close to L by restricting s to be sufficiently close to A on either side, but not equal to A, right? It's not necessarily defined at A. You're looking at near, in the neighborhood. So some open interval containing the A. Okay, please, any questions on this? So that's the definition. Anybody needs time here?
Yeah, can we like a couple more seconds on the slide?
Sure.
Thank you.
You are not unwelcome.
Thank you.
You're welcome. Okay. So now let's see how you write the notation. Now for this class, we'll be using this. So we stick with this notation, but there are other ways in which they can write it. So you can write it as f of s and then arrow L. So f of s approaches L as s approaches A. So you can write it this way, right? So that's one thing you have to know. Okay. Anybody needs time here? Now, for the last thing that they talked about, this part, I'm going to explain it using these graphs. So for this graph, right, we have three graphs here, right? So you have a function, you are taking the limit as you approach A, right? All of them, you are taking the limit as the function approaches A. But let's try and throw more light on this near A thing, near A. What do you mean by near A? So as I was saying, the function need not be defined at the point A. It doesn't even necessarily have to be defined, right? We are not interested in the exact point A. You're interested in the neighborhood of A. So let's look at these three functions. For each of these three functions, the limit as s approaches A of the function is L, but the functions are not the same. They are different. For the first function, is the function defined at A? Yeah, the function is defined at A. The function value at A is L. Okay. But then let's track the limit of this function as you approach A using the graphical method. So from the left, going up. Okay, so I can track it and see A is L. From the right, going down, is also L. So the two are also agreeing on L. So the limit of as s approaches A of f of s is L. For the second function, is the function defined at A? Yes, the function is defined at A. The value of the function at A is this, right? The value of the function is something smaller than L. It's smaller than L. But the question is, what is the limit? So from the left, going up, that's also L. From the right, going down, that's also L. Remember, when you're looking at the limit, we don't take the value, necessarily take the value of A, right? It's not the value at the A. So here, f of A is not equal to the limit as s approaches A of the function. You see, here, the limit here is still L, but the f of A is something below L, right? That's the shaded dot here. Please, are you okay? In the first case, the value of the function at A was equal to the limit. But for this second case, the limit is different from the limit is L. The value of the function is something less than L. They are not the same. So this is telling us that when you're doing the limit, please, it's not at the exact point. It's the nearness, right? In the neighborhood, not at the exact point necessarily. So for this one, the limit is L, still L, but then the function value is something less than L. Okay, now let's look at the last point. For this last graph, is the function defined at A? What do you say? Is the function defined at A? Anybody? No. Yes, that's true. The function is not defined at A. Yeah, the function is not defined at A because you see a punched hole here. There's a punched hole. you can't read the value of A. So for this graph, right, f of A is undefined. But the fact that f of A is undefined, does it affect the limit as you approach A? Well, let's see. Using the graphical method, as you approach from the right, oh, this is L, right? As I said, never cross the A. Look at more like getting towards A. So we are getting closer to L. As you approach from the left, that's also rising and rising. Oh, that's also getting closer and closer to L. So the two agree on L. So the limit is also L in the third case. However, the function is not even defined at A, right? So these three cases are telling us that when you're looking at the limit, you're looking at near, not exactly at the point. It could be that the function value at the point is the same as the limit. That's fine. But it's also possible that the function is not even defined at that point. And so the limit can be found. It's also possible that the function is defined, but it's different from the limit. But the emphasis is you're not looking at the exact point. You're looking at the neighborhood. So this is a very important conclusion. Please, are you okay with this? Yeah, the point is open on the third one. It's open. Right, yeah. Please, any questions here? Okay. Anybody needs time here? Okay, then let's move on. So now let's look at this other function. So this is another example. It says guess the value of this. So at this point, you are still guessing, right? So what do we do? Now, you notice that when you plug in 1, you get 1 minus 1 over 1 squared minus 1 equal to 0 over 0. The function is even undefined. The function is undefined for this, right? It's undefined. But does it stop us from finding the limit? Well, it doesn't, because when you're looking at the limit, you're looking at in the neighborhood, not at exactly that point, right? So what do? You can do the numerical method, right? So we can try numbers less than 1, right? So from the left, this one is from the left. Right, you're taking the limit as you approach 1. So we try numbers less than 1. So that's 0.5, 0.99, 0.999, 0.999, so on, and check the numbers, right? So see the pattern. You can also take values what bigger than 1. So this one is from the right. So let's check. So from the right, don't forget that you're taking the limit as you approach 1. So from the right, you're looking at something like 1.5, like 1.01, 1.0001, 0001, and so how many zeros you can say, and 1, but never use 1, right, for the numerical. So that one too, let's see the pattern. Now the most telling ones are usually at the end, right? See the pattern and look at the end. So looking at these two values, what can you say the limit is? Anybody? Looking at these two.
0.5.
Yeah, perfect. You can guess and say your limit is 0.5. So you can conclude and say the limit as s approaches 1, our guess, right? Our best guess for this function is s minus 1 over s squared minus 1 equal to what? 0.5. So that's our best guess. Please, are you clear on this? Okay. Any questions here? So that's the numerical technique. As I said, you won't be doing this, right? It's just a start to see how we are obtaining the limit. But later on, we will develop much more precise ways of finding this. Anybody needs time? Any questions on this? Okay. Now let's look at, oh, okay, it even brought it in. Now let's look at the graphical way, right? So for the graphical way, so they have the graph here, right? You have the graph here. Now let's use the graphical approach to check this. Now ignore this function for now. This graph that you see here is for s minus 1 over s squared minus 1. That's the same function as this one, right? What you see here. Okay. So for this one, we know the function is not defined at 1, you see. That's why there's a point tool here. There's a point tool. F of 1 is undefined, right? Because if you plug 1 in, you get 0 over 0, which is undefined. But let's track the limit using the graphical technique. We've already done the numerical way. So with the graphical, as you move from the left, right? Approach from the left, it's going down, down, down. Oh, the limit is approaching 0.5, so right? The function is approaching 0.5. What about from the right? Oh, it's rising, rising, and getting close to this. Oh, that's also 0.5. So the two are approaching what? 0.5. So from this, we can say the limit as s approaches 1 of s minus 1 over s squared minus 1 equal to 0.5. The same conclusion that we got with the numerical technique. Please, are you okay with this? Okay. Any questions on the graphical thing? Okay. Now, let's modify the function, this function a bit, right? So the initial function you're looking at was s minus 1 over s squared minus 1. So how are you modifying it? You are just modifying it so that it's defined at 2. Sorry, it's defined at 1. Right? Here it's undefined. The original graph is undefined at 1. But let's modify the same function, right? At that 1. We are saying that the function is defined and is 2, right? G of 1 is 2. So it's defined. If we define the value at 2, does it change the limit? That's the question. You've already learned that it doesn't change the limit, right? So this is the graph for the G of x, right? This one is the same as this, but they just define the value at 1 as 2, right? That's what you see here, the point 2. But still, if you are finding the limit, how do we get it? Using the graphical technique, right? From the left, you see the function is decreasing, decreasing. When you get here, please don't read it from here, right? It's not the value at 1. It's as you approach this, what is the function approaching, right? So that's 0.5 from the left. And then from the right to, you are rising, never read it here, not exactly at this point, but look at the behavior of the function as you approach it. So from the right to is also 0.5. So the two are agreeing on 0.5. So you say the limit of this function, of that G of x function, is still 0.5. Even though the function is now defined at 1 to be 2, the limit doesn't change. Right, so it's still emphasizing that when you're looking at the limit, it's not at the point where you are approaching it. It's in the neighborhood, like near that point. That's what you use to get the limit. So that's what this is saying. This is the important conclusion here. Please, any questions on this? Anybody needs time here? Right, so that's what I'm saying. This new function J still has the same limit as s approaches 1. So are you only focused on the s-axis? Yeah, so for the limit, right? Recall that you're trying to find the limit as s approaches 1. So the first thing you do is look at the s-axis to pick your point of interest. So you're interested in limit as you approach 1. So you obtain that, oh, 1 is here. And then you track the function, right? Don't forget you're taking the limit of the function. So track the function. Oh, for this one, as you approach this one from the right, then you track it and see where the function is approaching, right? So the x-axis is just to locate the limit where you're approaching. But then the rest of the job will be focusing on the graph, DC, which represents the G of x. Please, are you okay on that? Any questions? Okay. You're welcome. Okay, so that's it for that one. Now let's look at this second example. This one says estimate the value of this. So we are still on numerical and graphical. And as I said, you won't be doing numerical, right? The graphical way will stick with you, but the numerical is just for us to start with something to see what is happening. Now, this one is one of the pitfalls of numerical technique. Let's see what's happening. So for this one, if we ask you to obtain the limit, right? So as you approach 0, you try values on this side, you try values on this side, right? So that's why you see the plus and minus. So they're doing, say, -1 and +1. They're doing -0.5 and +0.5, and so on and so forth. Now, for each of these, they are getting closer and closer to 0, right? So the last thing they tried was what? 0.01 and then -0.01. Now, looking at the pattern, you see the number is like 0.1666666, right? So it's safe to say, well, from there, I can conclude and say, looking at the numerical technique, I will say this limit is what? 1/6, right? 1/6 is 0.1666666, right? So you can guess that this is it. But the thing is, if you had made a mistake and then taken more smaller numbers of the t, let's see what is happening. If I had taken much more smaller numbers and went beyond, like I did 0.001, -0.001, and so on and so forth, you see I'll be getting 0. I'll be getting 0, right? So does that mean that the limit is 0? Right? Well, it's false. The limit is not 0. The limit is actually the 1/6 which you got, right? But your calculator is what gave you the false values, because the calculator will approximate. And then as you approach 0, like as you approach 0, very, very small numbers, this thing here, the square root of that number will take it to be 3, rather than like a 3.00001, which is making the difference, right? It will take it directly to be 3. So you end up with like 3 minus 3, which is 0, over something small, which is 0. That's why it's creating this, right? So your calculator could give you issues with approximation when you take it too close, right? That's one of the pitfalls of the numerical. Now you can see more of this using this link. Lies my calculator and computer told me, right? I think it's 11:50. So let me end here. Do you have any questions on this one? Right, so that's one of the pitfalls. So on Monday, I'll continue with the third example. Yeah, so thank you for your time. All the best. If you get any issues, send me an email, use WebAssign question, ask my professor and stuff. Yeah, so that's all. All the best. Have a great weekend. You're welcome.
Thank you.
You're welcome.
Have a good weekend.
Same to you. Same to you. Have a nice weekend. So the first homework is due, I think, on Tuesday. The 2.1
Tuesday,
is due
yeah.
on Tuesday. And then 2.2, that one it became available today. So that'll be due like maybe somewhere next week or something. I don't know. I'm not sure. Maybe next week Friday or the Tuesday next. Yeah. Yeah. But check the deadlines. Yeah.
All right, thank you.
You're welcome.
It's okay to ask than to make assumptions. So for instance, yesterday, Mike's 2